Hello, everyone. My name is Anaya Carter, and today we'll be going over Lab 2 projectile motion. The contents of this presentation includes the introduction, which ultimately shows the purpose and all fundamental things for this lab, the main physics ideas, which consist of the main physics laws as well as formulas used for this lab, procedure, ultimately how I was able to finish the lab, analysis, which will be analyzing the predicted and observed data through the computational model, possible errors that could have happened during this lab that affected data, and also our final discussion questions. Okay, so for the introduction section of this lab, we see that the two purposes, ultimately, firstly being observe and analyze the projectile motion of an object, with this object being the paper ball, and the second being to compare motion in computational models with and without the component of drag. Our key assumptions for this lab is that gravity and drag are the only forces acting upon the system and that gravity is constant. For this lab, the system is the paper ball and the surroundings is everything else in the environment. So the main physics ideas for this lab was identified to be four things. Firstly, Newton's second law with the velocity update formula, position update formula, gravitational force, and also drag force formula. Especially as we were comparing the graphs with one with gravity, and then the second one being with gravity and drag. The drag force formula was a very pivotal formula for this lab. Yes. So for this lab, there were ultimately three main steps for the procedure. Firstly, to observe and record a video of the motion of an object that is thrown in a with projectile motion. And the second being to construct two computational models, with the first being including gravity and the second one including gravity and drag, with this being using glow script. And the third being to compare the observed and predicted data together in one graph. So in one graph, there would be the observed data that we got from tracker, and then plus two additional lines that show the predicted data through using GoScript, one including gravity, while the other one including gravity and drag. For this lab, we see firstly going over the tracker analysis. The total time for this analysis was 0.544 seconds, with the initial position being negative 8.597, and the with y position being 0.882, z being 0 meters. Initial velocity calculated to not be zero. This is also due to one of my possible errors in the lab, where I started the tracking at a point where the ball was not at rest, which is why also the initial velocity is not zero. For the computational model, I use both the velocity update formula, which is the momentum principle, as well as the position update formula. Also setting B or drag to zero, which allowed which allowed only gravity to be applied in this model, and we see the picture of how it looks as well. For the computational model, including drag as well as gravity, the B or drag changed to having a value, as well as the component of drag actually being able to be calculated, getting the magnitude of the velocity included within the drag formula, to add together with the gravity component for FNet. So this is ultimately the final graphical comparison where we see the blue being the observed, the data that was received in tracker, and then the red and pink or purple being the predicted, which was calculated through glow script. The calculated data is actually very much closer than the observed data, which can also be influenced by possible errors during the lab as well. For the possible errors for this lab, I identified two. Firstly, being outside forces, so anything, whether that air or anything that wasn't um, taken into account or contributed in the calculations could skew them, and also position tracking as the data is like the points are placed by hand. This can also skew the consistency of the data a bit as well. For our discussion questions, we see the first one being, do any of your models predict a terminal velocity? If the answer is no, what similar experiment could you design to find the terminal velocity of your object? So terminal velocity also occurs when drag is zero. So we see terminal velocity also happening in the model where there is zero drag, and this is also because forces balance out for F net to become zero. The second discussion question being, imagine if the object were initially thrown straight up with the same initial speed as in your experiment. Would the time this object takes to reach the ground or floor or table be the same, longer, or shorter than the time it took in your original experiment? So the time that it would take the ball to reach the ground would actually take longer, and that also being because in the original experiment, the force in the y direction wasn't as exaggerated as it would be if you were to throw it directly up. With all the speed and force being in the upward direction, it would take more for it to be dragged down and slowed to zero by gravity. Thank you all for watching and listening to my presentation. I hope you have a great rest of your day.